And hopefully I don't sound like an idiot up here tonight. I have severe jet lag. But this is how much I care about citizen science. We planned the citizen science and cocktails from the day I got back from an epic 18-day journey to Italy. So hopefully I don't say anything really stupid right now. So I just want to welcome you all to the Naturalist Museum. I'm the manager of Citizen Science, Leila Higgins, and I just want to say that it's really awesome to see so many people lost in our 2014 fall series for Citizen Science and Cocktails. Before I introduce our esteemed speakers, I want to tell you a little about Citizen Science here at the Naturalist Museum, which is generously supported by Time Warner Cable. We look at citizen science as a way to get non-scientists involved in the scientific process, a way to get our scientists to help them answer the questions they have about nature here in Los Angeles and around the world. Can I get a show of hands how many of you have participated in the Citizen Science Project before? Awesome, that's a lot. Can someone yell out one of the projects they participated in? Tree Tracker, yes, what we're all here tonight for. I didn't hear that. What was that in the back? Bioscan, yes, we've got a Bioscan site host here. Rascals, the reptiles and amphibians of Southern California. I see Dr. Greg Corley clapping in the back. I also am clapping on the inside. Thank you all for being citizen scientists and helping us answer those questions. So this past August, here at the Naturalist Museum, we were one of the sites for Tree Tracker, and as the citizen science manager here, I get to participate in a huge number of citizen science projects. And I can honestly say that Tree Tracker is one of my favorites. And this is a lot because I'm a super massive insect geek. I studied entomology, I have a degree, I Instagram pictures of insects, I put them on my face, really big ones, I have them as my profile pictures, Facebook. And so the fact that I like this project a lot, it has nothing to do with insects, really does say a lot about how much I think it's a really great project. And the reason I find it so compelling is because I feel that through this project, I'm helping to build a better Los Angeles. I feel like the trees that we monitored back in August were really helping to understand what trees are going to help to build a better Los Angeles, to figure out which trees we should be planting and where, and that will help to make a more livable city. And I have a lot of friends in Los Angeles who are really trying to make a change, and most of them don't work in the biology field, and they call themselves Changelinos. And so I'm like the one Changelino that's really focusing on bugs and plants and nature. And when I talk about Tree Tracker, it's the project that they really understand. They're like, oh yeah, urban heat island, shade, trees, yes, that's something we need. And so that's another reason why I really enjoy working on this project, because I can really sell it to my friends, and they really start to understand it. But to really introduce this project, I want to introduce two people who were instrumental in making this project happen. Dr. Mark Chandler from the Earthwatch Institute and Dr. Darrel Jenerette from UC Riverside. First, let me introduce Mark. He's the International Director of Research Initiatives at the Earthwatch Institute. He's the lead staffer from the Boston office on Tree Tracker program. And he's a firm believer in citizen science. So much so that he used to work at the New England Aquarium and was making exhibits about nature and science and getting people excited about the marine creatures of New England and all over the world. But then when a job came up at the Earthwatch Institute that was really focusing on citizen science, he made that switch over. I'm going to let Mark talk a little bit about Earthwatch and their role in Tree Tracker. So please join me in welcoming Dr. Mark Chandler.
Thank you. First, again, thank you so much for coming out tonight in challenging weather conditions. And I think it's sort of been interesting for us, we come from Boston, to be here during the 2 days where we've had more rain than at any other December 2nd, 3rd period in recorded history. And I think it's just a sign of the times here in terms of how much is changing. And this extreme rain event has sort of been on top of 3 years of record drought. And it's these kinds of huge grand challenges which are what Earthwatch looks at focusing our citizen science model in, which is really getting people out for not just a day at a time, but a week or 2 weeks at a time working with scientists all around the world. And Earthwatch supports roughly about 100 different projects in many different countries around the world, and roughly 3,000 people each year participate on these citizen science projects, whether it's urban water, whether it's looking at human-wildlife conflict in Africa, or urban trees here in Los Angeles. One question that I wanted to be able to look at is when we think about all these different places, Earthwatch has obviously worked in many different parts of the world, but Los Angeles and California in particular have a special place in what Earthwatch, who Earthwatch is and what we do. And one of the best representations of that is that through the generous philanthropy of some of our funders, we've been able to get out 400 different teachers to projects around the world from Los Angeles, and roughly about 300 different students on these different projects, and sponsoring them to be able to have experiences often for the first time leaving California and seeing parts of either North America or the world, and be able to bring back science, critical inquiry, understanding environmental issues, changing them into thinking about becoming a scientist or applying their professional lives to dealing with some of these issues. But one of the things that we hadn't really done is ever have a project in Los Angeles itself. And when there was an opportunity to try to bring our tree tracker project, looking at trees, into Los Angeles, it made a lot of sense to be able to connect up this amazing group of people who live in Los Angeles who get the importance of the environment, citizen science, and actually do something in Los Angeles. And the big idea is not only to start looking at the values of trees, and I think people are really starting to understand the value of trees in terms of energy benefits, in terms of cooling, maybe air quality. Trees reduce stress, they encourage play, people are healthier around trees. But it's the fact that trees are something that are really accessible for people. There's a nice term that I heard, I think, in meetings with the TreePeople, in terms of thinking about the sort of gateway drugs to a healthier lifestyle. And I think that's really true, and trees are something that everyone relates to. So it's a really powerful way to think about engaging people and making people feel that they can make a difference, which is true. At the beginning, I talked a little bit about the unusual weather that we're having, and that this is a sign of climate change. I think one of the things that's really been attractive for Earthwatch here in Los Angeles, that's also perhaps unusual, but certainly very powerful, is how collaborative groups are at trying to work together, how committed they are. The change that Lila is referring to has been something that's truly inspiring in terms of working here across many different institutions who all have a common purpose of making Los Angeles a better place. And I just wanted to talk very briefly about the partners who all came together in a relatively short amount of time to be able to look at how can we get people out across a large landscape to be able to help with citizen science. We worked with the Nature Conservancy, who was terrific at being able to identify key players and think about Los Angeles on a large scale. We worked with Amigos de los Rios, who have an emerald necklace vision for Los Angeles in terms of building green spaces, as well as Trust for Public Lands. We worked with schools, the Heschel School in Northridge. We're amazing at getting students and their teacher out, TreePeople, as well as NASA. And a big thank you to the museum for hosting us here and being a key player in terms of really coming together and all of this. And last but not least, I definitely want a big plug to thank Darrel Jenerette and Sherry Chevlet for helping in terms of really bringing the science piece to this. I'd like to turn it back over now to Lila to introduce our main speaker.
Thanks, Mark. So Dr. Darrel Jenerette is from UC Riverside, which is where I studied insects, my undergrad, so go Highlanders. Like many other scientists that I talked to, Darrel's love of nature was formed and nurtured through his early years on many, many camping trips and playing in nature. In fact, his earliest memory of the outdoors was a camping trip he took with his family to the Smoky Mountains when he was only 3 years old. Does anyone have any recollection of anything they did when they were 3 years old? I think that's really powerful there. And then at the ripe old age of 6, the family moved to a farm, and he spent hours and hours playing outdoors. And his love of camping really was encouraged by his family, and throughout his teenage years he began taking regular backpacking trips, and something that he still enjoys today. When it came time for college, Darrel chose to study biology at the Virginia Tech, and he said that it's really because they offered the most interesting courses, and it was a way for him to be able to understand the complexity of life that he was seeing all around him, especially on all of those camping trips. He went on to do graduate work in plant biology at Arizona State University in Tempe, where he received his PhD and then began studying trees in very hot urban environments. He's currently an associate professor at the Department of Botany and Plant Sciences at UCR and runs the Functional Landscape Ecology Lab. I did a little digging to find out what kind of speaker we have lined up for us today, and one of the first sites that popped up when I Googled his name was Rate My Professor. You'll be happy to know that we're about to hear from someone who received a 4.0 rating in helpfulness and clarity. He was described as a really nice guy and someone who is extremely passionate for his subject. Oh, and he also got a hot chili pepper, which means he's a hot professor. So, who knew that this was a factor for who you were going to pick to study botany from, but a lot has changed since I went to college, apparently. But all joking aside, we do have a very passionate speaker who's coming up and help me in giving a very warm welcome to Dr. Darrel Jenerette.
Good afternoon. Thank you for the opportunity to come here, Leila. Appreciate the ability to speak to you. This morning I was talking to 400 undergraduates in my introductory plant biology course. I think you are a much more receptive audience than a lot of them were this morning. Notwithstanding what Leila said, they say about me on Rate My Professor. I haven't actually looked there yet. So what I want to do today is give you a little background on my research, a little background on urban ecology, tie that together, and thinking about how does urban ecology shape our lives when we live in a city, and then get towards a lot of the research that was conducted this summer in support of the Tree Tracker program in Los Angeles. And that's sort of where I'm going to go with. I tried to minimize the amount of text on all these slides here. Normally when I'm giving a science talk, they're filled with texts, filled with lots of data, and I'm going to try to keep that to a minimum and make this more engaging. This picture here is one of the classic ones that I use on almost every talk. This is an image of the Earth at night. It's in composite around the globe. And from this you can see the lights of civilization. And just this amazing picture here just shows, you can easily see the outlines of all the continents, and the North America shines out brightly. You can see Japan, the whole island is just there. This is all urbanization. All of this light represents urbanization, the habitat of people. Now, in this decade, humanity has changed fundamentally. What had been for the whole history of humans a rural existence would now transition to more than half of the people on the planet live in a city. That's a huge demographic transition for people. And thinking about what it means to live in a city and how do we operate in this urban environment is critically important. At the same time, this transition is only beginning. And the projections are by 2030, there'll be another 2.5 billion urban residents. This transformation of humanity into an urban species is really just getting started. And within our lifetimes, within my lifetime, we'll be seeing just 2.5 billion more urban residents. That's a 65% increase in the amount of cities that we have right now across the world. So understanding what's going on in these cities is becoming more and more relevant to our lives and more important for understanding the whole world. And so that's been a big draw for me. I've got my work started in urban ecology when I started my PhD program in 1998. And at the time, I had no interest in doing urban ecology or cities. The idea of being an ecologist was to get away, and all of my cohort were like that. We were blessed at the time to be a part of a new funding strategy from the National Science Foundation. They had initiated in that year 2 new long-term ecological research sites. And there's about 20 of them scattered throughout the United States. In 1998, they founded 2 of these in cities. One was in Phoenix and one was in Baltimore. Now, the National Science Foundation and the ecological research community is thinking of cities as an ecosystem. Can we understand them as an ecosystem? Another big area, can we think about ecosystem in the city itself? So that both areas are that. And that's really propelled a lot of ecological research, a lot of understanding of how the world works is now focused through an urban lens, if you will. And that's really, I've been able to maintain that research, and it just keeps on being more fascinating. And I can think about really interesting science questions relating to a lot of just pure biology, pure leaf physiology kinds of questions. And I can also connect that to understanding how do people interact with their world? How do we make a more sustainable environment? How can we make choices that promote healthy living for all of us? And I think that's really exciting conceptually. At the same time, that's my research. Instead of going way out in the field and never seeing another soul, I can interact with people every day when I'm out in the field. I've been doing measurements at field sites in the city, and people have asked me, what are you doing? Are you making a movie? What are you doing? I'm like, no, we're measuring plants. Let me tell you about plants. People respond to that, and it's really exciting to be able to engage the public with science. I think that's a big part of the mission of being a university faculty member, to be able to promote science as an important thing. So take that context of urban ecology is becoming more recognized as a field of science, this growth of urbanization, and what do we start doing about it in terms of science? Climate change is a central part of my research in terms of this, and if you think about it in terms of an urban area, urban areas are getting hotter on the whole, and they're causing more risk to people around the world. And I think of this as being really the intersection of sort of three processes coming together. You have global warming overlaying all of it, so the whole world is warming up to one degree or another, and in urban areas that background warming is still happening, for sure. At the same time, we also have urban heat islands, where you have a city, you have buildings, those buildings are absorbing more heat throughout the day, and they're warming up the environment. We see a really strong urban heat island in just about every city that's ever been looked at. If you compare the temperature of downtown to the temperature outside in an outlying non-urban area, you can see a strong warming effect there. And then also with this increase in the urban population, this urban heat effect is growing because there's more urban areas as well, and it's impacting more people because they're in there. So this intersection between global warming and increasing urban heat islands and increasing urban population together is really causing an opportunity for potential increase in hazards from heat itself. And we've spent more than a decade now trying to think about that heat hazard and risk and the impacts of that onto vulnerability. This is from a picture that I think highlights really well what it looks like to be hot in a city. Driving on the freeway with the sun glaring at you. And some trees there hanging around. Hot temperatures in a city have a lot of important consequences. They directly impact human health, increase mortality and morbidity happens, as well as just general illness as well. It increases electricity usage. Los Angeles set the record in September for electricity usage in response to the heat wave that we had then. So this interaction between society and temperature comes out really strongly. Water use is another big one. When things get hotter, water use increases a lot as well. Whenever plants are transpiring or just evaporation. And the list keeps on going down there. We see increased crime when things are hotter, than plants are functioning faster, animals are functioning faster. Just lots of changes happen when things get warmer. And there's can we understand that warming process and potential ways to adapt or mitigate that has been a driving force of much of my research. And this is one of the data slides that I put together early on that's since been followed up in many cities around. This was from Phoenix where I was doing my PhD work. What I'm showing you here is, so this is all of the census tract boundaries. These are all the neighborhoods of the Phoenix metropolitan area. And the blue values are low vegetation. The high values are in red, high vegetation. So what we see in this downtown core is really low vegetation, surrounded by this ring of much higher vegetation. And so this is setting the stage of the spatial pattern of vegetation. There's lots of difference in where vegetation is located in the urban environment. There's lots of spatial variation there. This is the temperature map for that. Now there's using a satellite system called Landsat, which has been operating since 1970, which takes monthly images of the whole planet. We've been able to then get from those data the surface temperature. How hot is the actual surface as viewed from a satellite? From this, then, we can also aggregate this to the neighborhood level. What we see in this downtown core, again, is a lot hotter compared to this ring of much cooler where the vegetation is. This works out to a pretty strong correlation between vegetation and temperature that's in the urban environment. Where you have more trees, where you have more vegetation, the surface temperature is invariably cooler. And this effect is magnified in the summertime. So with more and more evidence, it's clearly showing that if we have more trees, the surface temperature decreases, and that can have an influence on vulnerability and potentially resilience to future heat waves. Another interesting part of this relationship that I found interesting, and I think really connects it in the urban environment relationship, is this is also paralleled with median household income. So here's this inner core here, where it's low income, they have much higher incomes, and it's surrounding this ring. You see this strong relationship between income, vegetation, and temperature. And you have this resource availability and the risk vary with income. And it's a nice segregation here, so we can think about like what's driving these patterns in vegetation, what's driving these risks to temperature, and how can we sort of influence some of these socially determined components of that. This is an example of what this looks like between this. This image here is a Google Earth image from above of a high-income neighborhood. This is from a low-income neighborhood. It's a striking amount of vegetation difference that you can see in these without much effort at all once you start looking through the data. This is one, everyone would pretty much appreciate it's going to be a much cooler environment there than it is if you're walking around here. There's a lot more safe places if you're looking to have a walking environment in this kind of place compared to here. And this is what we're trying to get into, is to understand what's regulating that sort of variation. One of the advances that we've been able to do is that rather than look at this neighborhood scale, which is what a lot of the satellite data historically has been limiting us towards, is now we can start looking at things at the individual parcel scale. And this is some work that we've just been completing this past summer, and it's winding its way through the publication process here. But here we have low-flying airborne sensors, which are mapping all of the urban area during the daytime. This is the neighborhood during the day, where the lower temperatures are in blues and the higher temperatures are in yellows. This gets up to 75 degrees Celsius high temperature, so that's like 140 Fahrenheit, something of that nature. Incredibly hot temperatures here. This is the nighttime image where it gets up to 35 Celsius, so you see this big swing between daytime and nighttime. These maps here are overlaid with the parcel delineations, so we can get information on the parcel itself and its temperature. We also now have this kind of classification that we can make from this imagery. We can classify this and get an idea of the proportion of vegetation and buildings and where that's located in a house, and you start understanding specifically at the individual household level what is happening and what's causing these biophysical relationships between temperature and vegetation or land cover, and how we can deal with that. We've also been able to take this information and conduct surveys with people, and then we've been able to lay over a household's temperature profile during the day and the night, its land cover, and then an individual response where they tell us, have you ever had a heat illness? And they can tell us yes or no. What do you think about your neighbor? Is it hotter or lower? And we've seen strong correlations between the temperature patterns and the percent illness in neighborhoods based on these kind of linkages of data sets from on the ground and from the air and from individual surveys. And I think that's a really exciting part of urban ecology, is being really able to drill down to the individual household, which is where the decisions are making, that's where impacts are happening, and expand that back out to the whole city and think about that multiple scale view of things. So that's really a big part of like what's driving my research, is trying to understand this vegetation temperature relationship. I've done a lot of work on that. There's a lot of uncertainties in there. This is one approach to trying to resolve some of those uncertainties, to really drill down. Another big approach, another big issue with these uncertainties is species variability. From the satellite view, it's just the amount of green. We know that it's not a very good proxy. Trees definitely differ, plants differ in what they do and how they function. Incorporating that species functional component is really important to improving our predictability and giving more informed management prescriptions for people to manage their households and their cities. So that's at one end. And more recently, we've really started been looking at this perspective too. This is Lake Oroville, recently in California. We have a drought. We are all aware of, I think, now in California. The water is at a premium. And in particular, this is another consequence of global climate change. More variable precipitation, more frequency and intensity of droughts is the most clear prediction of climate change. So we have these two components happening in climate change that relates to urbanization. We have this warming, it's getting hotter, and we want to deal with that hotter and come up with ways of keeping the environment cooler. And planting trees is certainly a key strategy in that. We know that it can cool things down, we know that it can have positive impacts on people's lives. The other end, trees require a sustainable supply of water. So how do we balance that out? And that's for me where I think a lot of the interesting science comes into it. It seems like there's a lot of how do we pick what trees to plant? How do we arrange those trees? How do we minimize the water costs and getting the benefits that we want out of it? Is driving the current research in my group, and I think there's a lot of interest broadly in this, is how do we think about trade-offs? And I think that's one of the real take-home messages I want you to come away from this talk is when we want to make decisions about our urban environment, we want to make choices that are leading towards more sustainable futures, we need to think about trade-offs. All the actions that we want to do have other consequences, and we need to understand them and manage them before we get. If we use a strategy that only requires trees and then depends entirely on water, it becomes vulnerable to droughts. And so we need to think about it. And I think that's where interesting science for me comes in, is balancing that heating and that water use. So this is Los Angeles. Now I've been in the LA area for about 8 years now, and we've studied the urban forest almost the entire time since I've been here. We've thought a lot about this. This is nice picture of the region. It's a very green region. Historically, it's not been this green before people came. People had a big part of adding trees to this environment. During our first research into this, we did a survey of trees in Los Angeles as a first just cut for what's out there. We sampled about 300 plots in LA City itself, and this is the distribution of those plots, and the size of the circle here corresponds to the percent tree cover of the plots here. And then the background of this is median household income. Again, we see a lot of variation in the plot estimated amount of tree cover. This, again, as in Phoenix, tree cover corresponds really well with income. If you have higher income neighborhoods, you have more tree cover. We see this all throughout the Southwest. We had research that came out just last year that's showing it's consistent everywhere in the Southwest. Along with this, we did a lot of biodiversity analyses. Biodiversity, interestingly, is contrast with this pattern in LA, in that it's in the older neighborhoods that we see the most tree biodiversity overall. It's not so much the income-driven component here, which we thought was really interesting in terms of a management perspective. If you want to increase ecosystem services, increase cover, you really need to target low-income areas. If you want to increase tree biodiversity, you need to target older neighborhoods in Los Angeles. We found in this survey 214 tree species from these 300 plots, which we estimate from that there's about 500 tree species native to this area. There's around 20 tree species. It's a massive amount of influx of species. These species come from all over the world. They're tropical, they're northeastern, there's northwestern, African trees that come from all over, which is amazing. We've been doing a comparison now between Los Angeles and many cities throughout the United States. If you look at something like Minneapolis, Minneapolis has only trees that grow around Minneapolis. They're very constrained, and that's a part of that. They're in a very cold environment there. Here, we can grow everything, and it comes out in our tree diversity. They're really, I think, what regulates that tree diversity and what is the implications of that tree diversity is a great science question, and it's a really great policy question. What do we want from tree diversity? What do you want from tree diversity? Would be, I think it's important to think about. They provide services, and then as well as in they're intrinsically valuable at the other side. So, given that, context. In this past summer, many of you participated in a tree tracking project in LA, and a big part of that activity was corresponding with NASA was doing an overflight of both thermal temperature and hyperspectral imagery for the region. This is their aircraft for that. This is a recommissioned U-2 spy plane that used to fly all over the world and try to track whoever was out there. And now NASA uses it for environmental research. This plane flies at 70,000 feet. The pilots have to wear effectively a spacesuit before they crawl into the thing. And then they'll fly over Los Angeles. They did this 3 times last year, 3 times in 2013. And I have good news for you today. As of this morning, I heard they will also be flying again in 2015. So we'll have opportunity to do more research. So that's really exciting, actually, that we'll be able to expand on the work we did and really learn so much more from this. And NASA is certainly excited about this opportunity. As part of that, this is a picture of many of the tree tracking participants. That's exciting. I really appreciate your effort. This is I've done a lot of urban ecology, and I've worked with people. This is my first citizen science experience, and it's just been overwhelmingly exciting. We were able to collect so much more data than even possible. Just out of my lab group, we had Sherry Shiflett, Dr. Sherry Shiflett is with us today. She's really done a lot of organization from our science end on how this is going. There's no way she could have visited all these trees at the same time and collected these samples that it just would have been impossible. The important part of this is we want to collect tree samples at the same time that these flights are happening overhead. So the idea is that we can compare what we see on the ground to what this airplane imager is seeing. And then can we effectively scale out to the whole metropolitan region? Can we get an understanding about tree functioning, tree diversity through that multiple scale comparison? So we appreciate your effort, and we think this is really exciting, and we are looking forward to continuing for the next several years and trying to learn about what's going on with trees from a basic science perspective and how can we manage them and get what we want from them. This is some of a summary of what all of you accomplished. We sampled in 10 parks. It included 130 volunteers sampling. You sampled over 400 individual trees and recorded 67 distinct species. That is an amazing amount of work over a 2-week period. And then it's corresponding with these overflights. So we're just overwhelmed with what's due, and we don't have much or any more data here to show you. It should be a couple more months to come out from this. Just processing all this information it's been daunting, but something that we are really excited about doing and getting into. So this is an example. I love this picture that Hite took of someone participating in the tree tracker program. And part of this, the citizen science can be accessible to just about everyone. I think that fits in with my mission of promoting science and doing urban ecology and getting people engaged with science. Not only just to learn about it and think about it, but this person, this child here, is contributing to science. And I think that's what citizen science can do, is we can engage in the process of science, contributing to data, thinking about interactions, thinking about hypotheses and predictions and testing them, and just that whole scientific literacy comes through with that, and this engagement. She's interacting with a tree, so it's actually in the natural world too. I think that was really powerful for me to see this happen. This is just one of several refrigerators filled with leaves that were collected. This thing was overflowed. We were scrambling, trying to find them. It was just packed in there. Within a week, these were all processed. Let's do an initial stage. So first thing that we wanted to do was to measure them for their leaf area. We want to dry them and then weigh them, and that gives us the leaf density. That leaf density is a key metric of plant functional components. And so that measure, leaf density, corresponds with so much plant physiology we can project from there. Another variable that we're trying to get, and we're in the process of, which is not surprising with 400 tree samples, taking us a while, is leaf nitrogen content. So we're trying to get to that point. This is us measuring leaf area as part of our leaf density part. Here we are on this scanner here. The leaf runs through, and this tells us how much area was on that leaf. And we can process a leaf within 5 seconds here. This is one of our undergraduates working furiously, 2 graduate students and our lab technician, all of us working together, and Dr. Schiffler really organized this and made this happen, got the whole lab working in succession in response to this. We want to get them to the state where we can dry them and then grind them up so we can do leaf nitrogen content. The key component of grinding them up is this action here of pouring liquid nitrogen into a mortar and pestle. This freezes them, and then we actually just grind them up manually. So it's kind of a slow and laborious process. You have to just grind away and get that and use the liquid nitrogen. After that, then we will send them off to a lab on campus where Dr. Schiffler or another graduate student will actually run the analysis for leaf nitrogen content. And that should be done in a couple months here. Here's a close-up view of what this slurry looks like of the liquid nitrogen and with the leaf as it gets slowly ground up into a powder. These are our scientists, both a postdoctoral researcher and undergraduate coming together, and I think this opportunity here brings it well. We can have the education continually going from faculty to postdoctoral scientists to graduate students, undergraduates, citizen scientists. The whole continuum is being met through this activity. I also find that incredibly rewarding. So this is where we are now. So we've got these leaf density measurements are coming together, and we're compiling them. The leaf nitrogen data are coming together, and we're still running those analyses to see where things are going. And in response to that, we're starting to learn about this. We're making a variety of plans for next summer with the news of NASA's next series of flyovers. We'll be able to expand on what we've done and really target it. And we're really committed to getting the most we can from last summer so we can update our methods and be adapted to what happened from last summer before we go into the next season. So there's a big push for that here. So I'd just like to end with this picture, thinking about science and what brings me and us to the work here. I was trained with this diagram before, and I've shown it just about every graduate student that's walked through my lab. This is how we can, in some sense, conceptualize why people do science. Is it a quest for fundamental understanding? Is that a motivator for you? Is that a high or low motivator for you? Or is it a consideration of use? Is that a high or low motivator for you? So if an individual does not care about use, but it only cares about the quest for fundamental understanding, that is the pure basic research. That is exemplified by Niels Bohr. He wanted to understand the atom. He wants to understand the physics behind it. He doesn't care how it gets used and was shocked at some of the uses for sure with this knowledge. But his interest was in, can we understand what's going on with the atom? At this other end, we have Thomas Edison, an excellent engineer and scientist. He wants to make a better light bulb. He doesn't care how that light bulb comes together, what's the fundamental components of the filament that makes that light bulb. He just wants to make a more effective light bulb and make it work. And that's his consideration of use. Up here in this past year's quadrant, that's where I train students and I try to position myself, and I think the citizen science really lets us dive into it here. Is this interaction between this pure basic research, this quest for fundamental understanding. What is really driving that trade-off between temperature and water use at the leaf level? There's a lot of interesting physics and chemistry and biology happening right there. At the same time, what can we do with that? How can we manage our cities better to get to a better place where we can have a better society and everyone benefits from that? This is exemplified by Pasteur. He wants to understand what causes disease. Germ theory comes from Pasteur. He also wants to cure polio. The polio cure comes from Pasteur. And so this intersection of pure research and applied research is, I think, exemplified by Pasteur, and that's where I think I want to go and help convince you it's an exciting place to be. So with that, I appreciate your attention, and I'm happy to answer any questions.
If you all have any questions, right here.